Hi there. So right now what I'm going to speak about is section 4.1, which is an introduction to exponential functions. Okay, so some key things to keep in mind is there's definitely a very big difference between linear functions versus exponential functions. Okay, and I'm going to emphasize that especially in the first example. But what I would like to say before I even begin, for linear versus exponential functions, linear functions will either grow or decline by some constant amount. So it's either plus or minus some constant number. Okay? Now, the way we contrast that with exponential functions is, again, we can still increase or decrease, but now we're increasing or decreasing by a relative amount. In other words, by some percentage. And it's really important to contrast those differences, okay? Because you see, if a population increases by, say, 100 people per year, that's going to be the same every year. You're just going to add on another 100 people. And that's different than saying that a population increases by 10%, because the first year you're going to be taking 10% of your original population, but then to compute the population after the second year, you're going to be taking 10% of a new population. In other words, you're still taking 10%, but it's of a different amount. And that's why we use the term relative amount. Now, I'd like to contrast that with the following example. Now, before I even start this example, what I'm going to say is my goal with this question is to develop what the formula for an exponential function looks like. In practice, you're not going to be doing a lot of these computations, but I want you to see where the formula or where for the exponential function actually comes from. Okay, so let me start this. Suppose we have the population of a town, let's say starts at 100, and let's say first that it grows by 5 people per year. Okay, I claim we can make a table showing the population. So here's the year, and here's our population. Okay? Now, in year 0, in other words, initially, you've got 100 people. 1 year later, well, notice it's growing by a constant number. It's growing by 5 people per year. So I know 1 year later, there's 105 people. 2 years later, there's going to be 110 people, etc. Right? 3 years later, 115. So there's a table showing us how many people are in this town after 1 year, 2 years, 3 years, and we can keep going. In fact, this is a perfect example of a linear equation. Remember, your slope is how much it's growing by. So it's growing by 5 people per year, and your y-intercept is your initial value. So, for example, initially plug in x equals 0, you're going to have 100 people. 1 year later, well, you have 5 plus 100 or 105, etc. Okay? So, here's a situation where it's linear because it's growing or alternatively decreasing by a constant number. Now, what I want to do is contrast that with this scenario. Now, let's say that the population of a town, we can still say it starts at 100 people. And now, though, let's say it grows by 5% per year. Okay? So, after we're done with this section, I assure you, you're going to be able to write out exactly what the formula is for the population of the town at whatever year. Okay? But what I want to do is just develop this so we see how these formulas grow. Okay, in year 0, yeah, we still have 100 people. Okay? Now, what happens after 1 year? Well, we have 100 people and it's increasing by 5% of those 100 people. Right? If it increases by 5%, remember, of means multiply. So it's 100 and then it's increasing by 5% of that 100. Okay? Now, in practice, you won't be doing this, but let me show you something. Do you agree that we could pull out the 100 here? Okay? This is where I say in practice you're not going to do it this way, but I'm trying to go somewhere with it. If I factored 100 out, because it's in each term, well, 100 divided by 100 is 1, and if I divide my second term by 100, I get plus 0.05. Okay? In other words, I have 100 times 1.05. Alrighty, well, if we care what the population is, 5% of 100 is 5. And so we're going to have the same number of people that second year. Okay? Now, a year later, suppose we want to know what happens in year 2. Well, don't we take that population of 105 and then it's increasing by 5% of that 105. So do you see how we're taking now 5% of a different number? So, in case you really care, we're going to have 110.25, okay? What's a quarter person? Well, I guess the baby wasn't fully born by the end of the year, okay? But that's not the point that I'm getting at. Let me show you something. Let me show you how we can factor this one. Again, we could pull out 105, and if I do that, I claim I'm left with 1 plus 0.05. Okay? Now, wasn't 105 equal to this amount? That's how we got 105. Again, just watch, because in practice you won't have to do this. So what I'm going to do in place of 105 is write the way that we computed it. That's equivalent to 100 times 1.05, and then this guy gives me another 1.05. Notice, don't I have 100 times 1.05 squared? Right? 1.05 times 1.05 is 1.05 squared. Now, yes, that's equal to 110.25. I don't really care about that. Let's do one more, and then I'll show you how we can deduce what our formula is. Again, I know I'm doing this strangely, just bear with me. Okay? So, now if I want to know my population at the end of the third year, well, what would I do? I would take this 110.25 and I would add on 5% of that. Okay? Now, I'm going to do the same funky thing. I'm going to factor out 110.25. And, again, I'll be left with a 1 in my first term and a 0.05 in my second term. Okay? Now what I'm going to do is I'm going to say, well, we can rewrite that as 110.25 times 1.05. Okay? But where did we get this 110.25? Wasn't that equivalent to 100 times 1.05 squared? and then I have this other 1.05. So the way we could compute it is 100 times 1.05 cubed. Let's start looking at the pattern that's going on here. Okay? Notice this one we could write as just, well, 100. This guy we could write times 100 times 1.05. This was 100 times 1.05 squared. For the third year, we have 100 times 1.05 cubed. Okay? Notice 100 appears. We could write this, by the way, as 100 times 1.05 to the 0 power. Okay? So notice the number in front here is my initial population. Okay? Notice that the exponent is the population, the computation of the population after that many years. So where did this 1.05 come from? Well, notice we get 100% of what we had, and then we're adding on 5%. And the way we express 5% in decimal form is 0.05. Okay? So I claim we could write this in general as the following. 100 times 1.05, we could say to the t power. And that's the population in year t. Okay? Alrighty. So, one thing that I would like to comment with just very quickly is when things grow linearly, they grow at a constant amount. When things grow exponentially, and you'll see it when we actually do graphing in a couple of sections here, they grow fairly slowly at first, but boy oh boy, when things grow exponentially, after a certain period of time, they start growing really, really, really quickly. That's why, for example, you never want to get into debt too much, because the interest starts growing exponentially, and that's why people get nailed with it. All right, now we can talk about decreases just like we can talk about things increasing. Okay, so let me take, for example, the following. Suppose we have a population, and now we'll say it starts at 100, but now let's say that it decreases by 5% per year. Okay? Let's start developing this formula. Okay? Now, I claim with this formula, we'll write him in black. It's still going to start out at 100, and we're still going to have the t there. The question is, how do we deal with this business in parentheses? Let's look. Do you agree after the first year you got 100, but now you're going to subtract off 5% of that population? So now if I factor out 100, I have a 1 in my first term, and now I have minus 0.05. Do you agree that's 100 times 0.95? Okay? And you will see as we build it up, after the next year, it'll be 100 times 0.95 squared. Okay? So, what's going to go in here is 0.95 to the t. Okay? So let me give you this general formula for an exponential function. In general, we can say an exponential function Q, which is a function of time, is a times b to the power of t. T is your exponent. B, first off, has to be greater than 0. Okay? So in general, an exponential function is a times b raised to the power of t, where a is the initial value. In other words, it's the value when t is equal to 0. Okay? If b is greater than 1, you have exponential growth. If b is between 0 and 1, you have what we call exponential decay. Notice when our population was growing, our base was greater than 1. And when our population was getting smaller or decaying, my base here, b, is between 0 and 1. Okay? If you have growth, b is equal to 1 plus r, where r is essentially the decimal representation of your growth factor. And if you have decay, b is equal to 1 minus r, where r again is that decimal representation. Okay, notice when I was growing by 5%, 1 plus 0.05 is 1.05. 1 minus 0.05 gave us the 0.95. Okay, so in this first section, what we're doing is we want to familiarize ourselves with these functions. So what I'm going to do is go through some examples now, just to reinforce this a, this b, the growth, the decay, etc. Okay? So this first example that I would like to do is as follows. Okay? I am going to give you a population of 6 different towns. Okay? I'm going to give you the formulas. So town 1, my population is given by this formula. 1,000 times 1.08 to the t. Town 2 is 600, 1.12 to the t. Town 3, I have my population is 2,500 times 0.9 to the t. Here I have 1,200 times 1.185 to the t. Here I have 800 times 0.78 to the t. And last but not least, here we have 2,000.99 to the t. All right, so my first question is, which towns are growing in size and which towns are shrinking in size? Again, that's where you look at the base. If the base of your exponent is greater than 1, you're growing. If it's less than 1, it has to be greater than 0, then it is shrinking. So I'll use G for growing, S for shrinking. This one, I claim it's growing. It's growing by 8%. This one is also growing. Okay, just knock off the 1, you got 0.12, so that's growing by 12%. This guy is not growing. It's less than 1. Okay, so he is shrinking. Well, what's he shrinking by? We have 0.9 is 1 minus r. Well, we can solve for r. Okay, you can do this in your head, of course, but you can solve for r first by subtracting 1, and you get negative 0.1 is negative r. So r is 0.1. In other words, this is shrinking by 10%. Okay, this one's greater than 1. It's growing. It's growing by 18.5%. This guy, notice it's between 0 and 1, so he's shrinking. Now, how do you get from 78 to 100? Isn't that 22? Yes. It's shrinking by 22%. And this one is shrinking, well, how do you get from 0.99 to 100? 0.01. In other words, it's shrinking by 1%. Okay? So, if I asked you which town is growing fastest, you would look at the growing towns and you would see who's got the biggest percent. I claim he's growing fastest. All right, and isn't the annual percent growth 18.5%? Now, what if I asked you which town is shrinking the fastest? Well, we have 3 towns that are shrinking. Who's shrinking by the biggest percentage? This town right here. Okay, now one other question I'm going to ask. I'm going to ask which town has the largest initial population and which town has the smallest initial population. Remember, your initial amount is the number in front. So I claim the town with the largest initial population is this guy. Notice he's going to be shrinking, but initially he's starting out with the biggest population. And the town with the smallest initial population, well, it looks like 600 is the smallest number in front. Okay? So that kind of gives us the general overall, how do we look at these things? Okay, the next example that I would like to do is as follows. Again, just to reinforce the meaning of these things, is what if I tell you this? What if I tell you that the value in dollars of an investment in year T is given by this? And what we want to do is describe the investment in words. Now, there's not a whole heck of a lot I'm asking us to say, but I am asking us to acknowledge what that 2,500 means and what that 1.0325 means. Okay? So, let's just go in order. What does that 2,500 mean? Isn't that the initial value of the investment? Initial value is $2,500. Okay? Now, what does this 1.0325 mean? Well, notice that my base is greater than 1, and therefore my investment is growing since it's greater than 1. Well, take this 0.0325 and put it in percentage form, and I claim that means it's growing by 3.25% per year. Alrighty. Next. Suppose I give you this, okay? Suppose I tell you that your initial amount is $2,000 and it's increasing by, let's do 7% per year. What I want us to do is write the formula for this exponential function, and then we'll find the value, and then what we'll do is we'll find Q of 10. Okay, so let's just say that the initial value is 2,000, and whatever this quantity is, it's growing by 7% per year. Using my formula, you write your initial amount. Notice it's increasing, so it's 1.07 to the T. Okay, so if you wanted to find the quantity or the value, whatever it is we're talking about, when t equals 10, well, literally, you would plug in 2,000 times 1.07 to the 10th power. Now, I've got my handy dandy calculator, and so I'm happy to use it, and what we see is 3934.30. Don't worry, on a test I'll always specify how many decimal places to round to. Okay? Now, let's take one more similar to this, but now let's say that our initial amount is, say, 35, and let's have it be decreasing by 8% per year. All right. Well, again, the first thing we do is we put our initial value. Now, since it's decreasing, don't we take 1 minus 0.08? In other words, we get 0.92 to the t. All right, and if we want to find the quantity or the value, whatever it is we happen to be looking at, 10 years later, we would compute 35 times 0.92 to the 10th power. Again, in case we really care, we can compute this, and we're going to get about 15.2. Notice, in fact, it did decrease. It started out at 35, and now it's smaller, just like this started out at 2,000, and that increased. All right, let's do a couple more examples here. Okay, this one reads as follows. It says a typical cup of coffee contains about 100 milligrams of caffeine, and every hour approximately 16% of the caffeine is eliminated. Or, well, the amount of caffeine in the body is metabolized and eliminated each hour. Okay? So, what we want to do in part A is we want to write C, the amount of caffeine in the body in milligrams as a function of T, which is the number of hours since the coffee was consumed. Now, the biggest hint that you have an exponential function as opposed to a linear function is, notice the amount that it's increasing or decreasing by is given as a percentage. Okay? That tells you it's relative. So, let's write this function, C of t. Well, notice all of our units match up. That's something important to check. Well, let's ask ourselves, initially, how much caffeine did we have in our body? In other words, when t equals 0, that's your initial amount, we had 100 milligrams of caffeine in our body. Okay? I know my exponent is going to be t. Well, notice it's being eliminated, so it's decreasing, so we would take 1 minus 0.16, or we would get 0.84 to the power of t. Cool, huh? Now, suppose, just as a follow-up, I asked you how much caffeine is in the body. We'll make this part B. after 5 hours? Well, all we do is we compute C of 5. So it's 100 times 0.84 to the 5th power. And we can certainly compute this. And we get approximately 41.82 milligrams. Alrighty, let us do one more example. Okay, this next example reads as follows. Grinnell Glacier in Glacier National Park in the U.S. covered about 142 acres in 2007. So in 2007, it covered 142 acres. And it was shrinking, bummer, at a rate of 4.4% per year. Okay, in part A, we want to write a formula. So we want to give a formula for S, the size of the glacier, in acres. Okay, as a function of the number of years, we'll call that T, since 2007. In other words, what we're doing is we're letting the size in 2007 to be our initial value. Okay, so what's my initial size? 142 acres. I know this is an exponential function. And since it's shrinking, we're going to take 1 minus 0.044. And we're going to get 0.956. Okay? Now, since we found the formula, we might as well answer a question or two that follows. Okay? So, what can I ask? Well, what if I want to predict the size of the glacier in the year 2020? Okay, well, remember, T stands for the number of years since 2007. So the first thing we have to do is figure out what our T is. Well, I think you'll grant me that T is 13 here, because 13 plus 7 gives me 2020. So we're going to compute S of 13, and that's equal to 142 times 0.956 to the 13th power. This might be really depressing. And if we want to, it is very depressing. It's going to be about 79 acres. Wah. Alrighty, so that gives us our general exponential functions. Again, taking and looking at our initial value versus whether there's growth or decay. All right, that completes this section. Thanks.